Hi, and welcome to this practice session with Bayesian SEM. We will use R instead of JASP because there is no module of Bayesian SEM in JASP. So we need to go directly into blavaan. Uh, you will need some prior experience with R. You don't need to have a super expert, and the script I have prepared is pretty straightforward. But if you don't have any experience with R, I suggest to first find a really simple tutorial to get the basics on how to install R and RStudio, how to execute scripts, etc. Okay, so moving on, this script has two parts. The first part will use the default datasets that are available in blavaan and blavaan. And also we will use default priors and everything to just get a quick solution and to showcase what you can do with BSEM models, what you can get out of them, and how to assess them. Okay, so I already have an environment, an R object that is already saved. And I will execute some lines to get the results out of it. So if you want, you can just upload the object. Also, you can execute all of the script by yourselves. Just have in mind that it can take a little bit. The first part, for example, like 30 minutes or 20 minutes for all of the first part to get estimated. However, the second part will use some empirical data that I also have uploaded from a real study. And because of the models for this data will be ordinal and also with two factors and more complex and more items, they can be really time intensive. For example, a couple of hours at minimum. So keep that in mind, and just feel free to explore more technical improvements to get faster computations and whatever. Okay, so first of all, we have this line that is the set working directory. I didn't have any paths because I will use the default datasets. But remember that there you need to put your path to the files that you have. Okay, so these are the packages that we will use: blavaan and blavaan to make SEM models and Bayesian SEM models, also Psych to create some things with the data, and also beeper, that is a short package, a very small package to make some sounds after something is a command is already finished. Okay, so first of all, this function is really good because the dprior function will inform you of which are the main parameters that you will estimate in a BSEM model. And as you can see here, we have nu, alpha, lambda, beta, theta, etc. Here is a list of all of the parameters that you have available in blavaan and what you can do with them. Okay, so if you want to go for informative priors, you can just start tweaking on that. Okay, so here's the model that we will use. That is the Holstein-White and Swine for 1938 dataset. So we have three factors with three items each: visual, textual, and speed. And here is the first Bayesian CFA that we will use. It has the model, the data, the target for the sampler is going to be Stan. You can use other samplers. We will see that later. And here is that save the latent variables. Here are some technical aspects that you can unlock if you want to. For example, 3 chains, 1000 samples with 500 burning samples and 100 from adaptive samples. You can have also an assignation of the cores of the computer that you want for the chains. Also, you can also have this nice tweak for a higher speed precision balance, and also a seed for reproducibility. And here is the beep function that you can use that to just get yourself reminded that something has finished. Okay, this is one of the sounds, and also has this other sound. Okay, there's a lot of funny sounds in here. Okay, okay, let's go. So we already have this model estimated. So let's first of all screen the convergence. So here are two functions to screen the R hat statistic. Remember, also Gelman-Rubin statistic, the P as RF, or the potential scale relation factor. So we have that here the parameters of our model are all almost in 1.0. all of below 1.1, so that's good news. And also we have here the effective sample size for all the parameters. As you can see here, pretty big numbers. However, none of them is above 10,000. So maybe we need to increase the number of iterations if that's necessary. Okay, so if we want more technical output, here is the raw values of all of the parameters for all of the chains if we need them. We also have the latent variables for all of the chains and all of the steps for all the subjects. And if we make an average on that, we can get all of the latent variable scores for all our subjects. We have 301 subjects, and we will have the average of the factor scores for each of our factors. As you can see here, visual, textual, and speed. Why an average? Because, well, we have a posterior distribution and with 3 different chains, and an average of all of that can become this factor score. Okay, so if we want to make some plots, we can create some trace plots for our model, and as you can see here, I will make them bigger to see. You can see all of our trace plots of our model, and everyone seems to follow how do you say, a caterpillar form, as you can see here. So apparently there are no major issues regarding this, so we can just move on. And now we can ask for more specific outputs. For example, here I will ask only for the 6 first parameters of the model density plots. Here, as you can see, it is no differentiating by chains. This is like the average density plot of the posterior for all the chains. You can also visualize them in histograms if you like. And I like this very much because it's a density overlay for all of the chains. As you can see here, there are some small differences in the parameters in the chain, so maybe we need to increase the MCMC steps. You can also do that with comparing all of the densities between them with the values, as you can see here. But remember that to compare them, you need all of them need to be how do you say, in the same metric. Okay. We also have histograms by chain. As you can see here, we have 6 for chain 1, 2, and 3. If you like that visualization, we also have Bayesian plots if you like them better. And here is a more extra plot. And finally, my favorite, that is a combo plot that will combine the visually the density curves for all the chains and also the trace plots, so you can, in a quick look, assess the representativity of the values. So that's pretty okay. So if you're interested also in the relationship between 2 parameters regarding the MCMC estimation, you can do that. For example, these are a scatter plot of the values of the MCMC regarding the factor loading for item 2 and the factor loading for item 3. You can also visualize that in hexagons, which I think they are so beautiful that maybe they can become a little bit difficult to visualize and to understand. Also, we have some pairs with 2 scatter plots and the histograms here. And oh yeah, so that's an extra if you are interested in screening these properties. Also, now we can have autocorrelation plots. So as you can see here, all of them are descending without little differences between chains, and also all of them are really near to 0. So that's a good thing. And also we can visualize them in bars. So we want small bars surrounding the line of 0. So it seems that there are good news regarding all of the steps that we have. Okay, so now that we have seen all of this, we can assume that the model seems to be okay. So maybe we can describe it. Okay, so here we have text information here for our model. As you can see here, we have the we have the optimization method that is used, the model test statistic, etc. Right? Okay, we can also create the interval plots for all of our parameters. that remember that they are not in the same metric. For example, the factor loadings are not going to have the same metric as intercepts or intercepts, so just be mindful of that. And also we can filter them, for example, the first 9 parameters, and here we have the point estimates for all of the parameters that we want, and also with some box plots that will reflect all of the variability of the posterior distributions, which I think is pretty okay and pretty good to visualize in this measure. Now we can create fit measures. So as you can see here, we have the log likelihood, the PPP, then we have the BIC, DIC, the widely applicable information criteria, the WIC, and also the LU IC. So now we can have some more information regarding fit measures. Okay, so now that we have this, it will be really wonderful to have the approximate fit measures like Bayesian CFI, Bayesian TLI, and Bayesian RMSAA. But to do that, we need a null model. So here is the model that we already estimated, but now we will create a null model that is over here, and that will just create correlations between items, and that's it, without any latent factors. Now that we can estimate that model with the same technique, we can create fit indices comparing the null model to our proposed model. And then if we create that object and also ask for a summary, it will give us this table that is basically our Bayesian RMSAA, the Bayesian CFI, and the Bayesian TLI, along with another ones. Then we will have a posterior distribution for all of those statistics, and we will have the EAP, the median, and the MAP estimations for the maximum of the posterior, and also the standard deviation with the credible interval. So prioritize the EAP in this case. So we have 0.099 for the Bayesian RMSEA, which is not ideal. It's not super terrible, but it's kind of mixed evidence. The Bayesian CFI is 0.93, so that is very good. But also Bayesian TLI is 0.88, so that's not good. That's not terrible, but also that's not ideal. So Bayesian RMSAA and TLI report some concerns regarding the model, and also CFI is reporting that is very good. So maybe we will need to have an extra scrutiny regarding our model, that, for example, increasing the number of the number of steps by chain, or making more informative priors or something like that to make the model to fit better if there's an available one. Okay, so moving on. Here are some alternative commands if you want to try another samplers. For example, the JAX, the stand classic, and the stand conditional samplers. I recommend stand just as it is because it's very powerful and very fast. But if you want to try, here are some commands that can guide you to make the necessary steps. Okay, so now imagine that our model is okay, everything is okay, the fit measures are okay, the parameters are okay, and we want to make some invariance analysis. So first of all, we can create the classic invariance analysis, but using Bayesian inference. So first of all, we will need these 3 models that are the frequency CFA to extract a parameter table that is basically the same information of the model but in a reduced format, and then create a Bayesian inference over them. And then we can have the group variable, for example, school. But now, in the first model, it will only take into account this variable, so it will create a CFA for each group, and that's it. Everything is free. The next level is going to restrict to be exactly equal all of the loadings of the models, and the next level is going to restrict exactly equal the loadings and the intercepts of the models. So here is the conversion into a Bayesian inference of these 3 models, and then we can take a look on the fit measures of these 3 models. As you can see here, we have the same BIC, DIC, PPP, WIC, LU, etc. And now we can compare them. For example, here we have the configurable model against the metric model, and we have a lower WAIC and also a lower LU CV statistic, and therefore we can conclude that there is an improvement of fit when we restrain to be equal the loadings of the model. So therefore, maybe the metric invariance can be assumed from a Bayesian point of view, but remember that we are not making an approximate measurement invariance, we are only making a classic invariance analysis. If we shift into a metric against scalar, that is restricting the loadings and the intercepts, we can see here that the WAIC increases its value and also the LU increases its value. So therefore, we cannot assume that the fit is better. Actually, the fit is worse. We don't know if it is worse enough to not assume or not be able to assume this level of invariance. We only know that it is worse. Okay. Okay, so now we can make then approximately invariance analysis in here, where we can say, here is the model, here is the data, here is the group variable that I want, and also in the next level, force to be equal the loadings, but then two commands will come into play. The wiggle command will say, from the ones that are restricted to be equal, let to be approximately equal the loadings and with a standard deviation of 0.1. Okay, and in the next level we will have loadings and intercepts as equal, but let them both wiggle, as you can see here, with a standard deviation on 0.1 and 0.1. Okay, so we will have a very informative approximate measurement invariance analysis, because I have specified that we will let them wiggle. We will let them to have a distribution of differences between parameters around 0, and also with a small standard deviation. Okay, so we will have a very informative prior regarding approximate invariance. So now we will have our raw fit measures. Remember that you can also create the Bayesian fit measures if you want to, and we can compare them. Okay, so as you can see here, we will have a similar result from earlier. Here we have a lower WAC and also a lower LU. This indicates that from approximate measurement invariance, this seems to be okay. It seems to be better. But however, here it increases its value, and also it increases its value in both statistics, although less than with the strict approach. So therefore, maybe if we specify a less informative prior regarding the wiggle commands, for example, standard deviations of 1 or 0.5, maybe the fit is okay, or it sustains itself. Therefore, we can assume an approximate measurement invariance regarding intercepts with a distribution of differences. Okay. Also, you can describe it, and also you can apply all of the other analysis that I have done previously here from a technical view and also from a statistical view. You can also obtain the BRMSAA, BCPI, and BTLI, etc. So yeah, that's a basic overview of what you can do with blavaan regarding BSEM models. And remember that you can do many other things. You can optimize it, make some thinning adjustments, or play with the iterations with the MCMC, change of samplers, and also, and the most interesting thing is to change the priors into more informative solutions. So yeah, this is the basic tutorial into blavaan. I hope you enjoyed it, and that's everything. Thank you for being here.